Today we are going to talk about the periodic trends and the reasons behind them. And I know you've memorized the periodic trends. So first let's start from where we were last time. So last time we were talking about the wave equations. And we saw this equation where we broke the wave equation or the wave function into a radial variation, which is defined by the radius, times an angular variation, which depends on the angle. So I showed you this table on a piece of paper. And what this is these are the actual radial functions for different orbitals. So the radial function itself actually depends on which orbital you're talking about. In other words, it depends on the L quantum number, and it also depends on the energy level, or the N quantum number. So this is a table that just shows you that. Figure 1.9 and 1.10 in the textbook show you the radial variation, or the radial wave function. So you can see that there's a positive and a negative part to, for example, the 3s orbital. So that's just the function. Figure 1.10 is just the 2p and 3p orbitals. If we go and look at the square of the function, technically this, hold on, let me get my pen out. So here we have basically, this is r, the function of r, and this is the radius squared times r squared. That's the radial probability function. But it's really just a constant times the function, so we can kind of think of it in qualitative terms as just the square of the r function, which is related to the probability function that we talked about, where the probability of where the electron is. So notice that the 2p orbital in both cases is positive in the whole function, but the 3p orbital down here is negative. Oh, we don't have the 3p orbital. I'm sorry. Well, the 2s. Let's go down this chart. This is a better example, and it's very small, but you can see here. So here's the 1s orbital. Oops. Yeah. Okay. Here's the 1s orbital. That's the radial function, and here's the probability function for that 1s orbital. So the more interesting ones are, let's look at the 2s here. This is the 2s orbital, and you can see that for the 2s orbital, you have a negative portion of the function and a positive portion, but when you square that, you have two positive portions. Where this function goes to 0, you have a radial node. So do you remember from any of your classes that the 1s orbital is just a sphere and the 2s orbital is a sphere, but it has a radial node within that sphere? Do you guys remember that? Okay. So in case you don't, let me just go to this website. This is the Orbitron website, and it's really useful for looking at the orbitals. So if I look at the 1s orbital, it just looks like a sphere. But if I look at the 2s orbital, it's a sphere inside of a sphere. So the radial node here, where the red is turning to blue, is basically the same as this node. Okay? So this is what I'm showing you here is a 1 or 2 dimensional graph, and then on the Orbitron website we see the 3-dimensional version of that. Okay. So that's the radial wave function. It depends on the radius. So that's why, if it only depends on the radius and it should be the same in all directions, that's why you get spherical nodes from these radial nodes. So the angular part of the wave function is on this table. Now this is a little bit more complicated, and your textbook doesn't actually go into this very much, and that's okay because it's hard to understand, and it's because the fact that these functions, especially these, have imaginary numbers in them, and so they're not real functions. But here is a visualization of what those functions, the function of the real part here would look like. And then they've done some mathematical manipulations here to make these real functions. And then you can see this, which is what we're familiar with, our familiar orbital shapes. So the shape of the orbital comes from that angular part. When you put the radial and the angular together, that's when you get what we know as the orbitals. Okay? So I just want to point out that as far as the nodes go, there's two types of nodes, radial, and those are where the radial function is equal to 0. These are spherical, and they depend mostly on the shell that you're in. So you will be able to know the number of radial nodes based on how do you know how many radial nodes there are? Based on what you know right now. So if you're in that 1s orbital, are there any radial nodes? No. There's a boundary surface where the function approaches 0, but it never is 0. Okay, so that's different than a node. So there's a boundary surface in the 1s orbital, but there's not a node. In the 2s orbital, is there a radial node? We just saw that there was, right? So there's a boundary surface and there's a node. So the number of spherical nodes is equal to n minus 1. But what about, let's talk about where n is 2, but L is 1. So the 2p orbital. Are there any spherical nodes in the 2p orbital? Let's look. Are there any spherical nodes there? There aren't any, right? There are boundary surfaces, but there aren't any nodes. What if we look at the 3p orbital? Are there spherical nodes there? It's harder to, it's a weird color. It's harder to see because unlike the 2s orbital that we were looking at before where they chopped it in half to show you, this one's a little bit different. There is a spherical node there. It's a sphere basically around those two little lobes in the middle. Okay? So there is a spherical node in the 3p orbital. You can describe the number of spherical nodes if you also consider L. So the number of spherical nodes is n minus 1 minus L. The other type of nodes are angular nodes. And this is where your angular part of the function is 0. Again, you can have angular boundary surfaces where that function's approaching 0, but it's not the same as a node. So these are usually planar nodes, and they depend on the subshell or L. So this is a picture in your textbook. This is figure 1.14. So those nodes that are shown there are angular nodes. Only a p orbital would have that node. So an s orbital wouldn't have this planar node, which depends on the L value. Here are the d orbitals. So the dz squared isn't exactly what we usually think of as a plane. It's more like a cone, but it's an angular node. It depends on the angle. All right, so we spent most of the time, or all of the time last class, talking about hydrogenic-like atoms, so 1 electron atoms. The last thing I want to talk about as far as hydrogen goes is the fact that the value of N gives you the energy. So there's an equation that's going to be useful to you, and it's this equation. So you already know that the value of N defines the overall energy for an electron. This is an equation for a hydrogen-like electron, or a hydrogen-like atom. What do I mean when I say a hydrogen-like atom? My P chemists should know this. You're in P-Chem with Dr. Barstick. What does it mean to be a hydrogen-like? Exactly. 1 electron. So this equation is only valid if you're talking about an atom that has 1 electron. you can talk about that electron being in the n equals 1 shell. You can talk about it being in the n equals 7 shell if you want. But it's an atom with 1 electron. So what are these? This HCr may be familiar to you. It may not be. This is Planck's constant. C is the speed of light. And R is the Rydberg constant. It's not the function R that we were just talking about. You can look up these values in your textbook, but I'm going to tell you what they are. Together, they add up to 13.6 electron volts. It's a lot easier to remember what those three are 13.6 electron volts than to memorize all of the different constants. This Z is the atomic number, or the charge. N is the principal quantum number, and the E here is the energy of an electron in shell N. So again, I want to stress that you can have the electron in a 1 electron atom in any orbital you want, or any value of N that you want, as long as it's the only electron. So N does not have to be 1, even though it's hydrogen-like. This is also the equation, so the equation that you use to calculate the energy of that 1 electron atom is the same as the ionization energy of that electron. So whatever energy it is, that's how much energy you would have to put in to get that electron out of there. So this is also the ionization energy. So that equation is going to be useful to you. There's a few equations that you'll need to use for your homework, and I know that there's a ton of equations when you're going through your reading, but the important ones are in your notes. All right, so let's now move on to many electron atoms and talk about periodic trans and electron configurations. Okay, so the first thing we're going to talk about is shielding and penetration. And this happens only in atoms that have more than 1 electron. Atoms or ions that have more than 1 electron. You have something called shielding, and you have another thing called penetration. So when one electron is present, when more than 1 electron is present, shielding and penetration affect the energy levels of other electrons around them. And I'm going to use helium as an example. So if you have a helium nucleus, I'm going to draw my helium nucleus in red. That helium nucleus has a 2+ charge. Helium has 2 electrons. But let's talk about when we just add 1 electron into this system. So I'm going to put my electron here. What charge does that electron feel from the nucleus? It's 1 electron and it sees a nucleus. What is the charge that it feels from that nucleus? What's the charge of the nucleus? It's +2. And if it's the only electron around, it feels that whole 2+ charge. So when you add the first electron in there, it feels the full 2+ charge. So this would be helium plus would be an example of this system where you have a 2+ nucleus with 1 electron. So the first electron feels the full 2+ charge. Now, what if I add a second electron in there? So now my helium atom is complete. What does that second electron feel? Does it feel a 2+ charge? Anybody have any thoughts? No? You don't think so? Do you think it feels a 1+ charge? Okay. So when you add the second electron feels less than a 2+ charge, but it feels more than a +1 charge. And it's because every electron that's in the atom already, it cancels out the positive charge a little bit, but not completely. So the second electron feels less than 2. And this is because the first electron shields the second electron. So the first electron basically it's kind of like a force field, right? Or you can think of it the true explanation is that this first electron, it's in the 2s orbital, right? And I'm scribbling to represent that orbital. If you have a spherical distribution of a -1 charge, you can treat that as a -1 charge at the point in the center, right? So this electron basically can be treated as just canceling out some of that 2+ charge. So it's important to remember, though, that this electron, oops, I'm going to change my color back to green. This electron still feels more than a +1 charge. Now I'm going to go and show you a picture. This is a table from your textbook. Here you have the atomic number, Z, across the board here. And this is the effective nuclear charge that the electron feels in the outermost orbital, or the valence orbital of that atom. So the hydrogen 1s electron, again, there's only one, so it feels a full positive charge. In the helium atom, the second electron feels only a 1.69 charge. So it doesn't feel a full 2+. It doesn't feel just a 1, because that first electron cancels out the positive charge. This is why we get contraction of atomic size going from left to right across the periodic table. So if you look from left to right across this periodic table, you'll notice that the atoms on the left-hand side are much larger than the atoms as you go across the periodic table. That's because each time you add one more proton to the nucleus, the electrons in the first shell feel more of a positive charge. So they are actually contracted. And every shell after that is also contracted. So the more positive the nucleus is, the more the first electrons feel that positive charge and are pulled closer, and the more the outer electrons will also feel that positive charge, because they're not, the innermost electrons are not shielding completely that positive charge. So shielding is the reduction of true nuclear charge to something called the effective nuclear charge. And this is given by the equation Z effective is equal to Z minus sigma. And this sigma is a shielding constant. It's an empirical constant. Do you know what that means? So it's different for each shell, depending on how many electrons are in the atom. And being an empirical constant means it's a constant basically that fits data. So it fits observations that we see. So this isn't something that you can calculate without doing experiments. So the closer an electron is to the nucleus, the closer the Z effective is to Z. So when you start off in the very first shells of the atom, usually of a many electron atom, your Z effective will be really high for those electrons. And so Z effective can be specific to whatever electron you're talking about. As you move out, the Z effective is farther from Z. So the larger atoms are, the smaller their 1s orbitals are in size. And because Z is high at the first shell, the electrons are held more tightly. So now let's talk about penetration. Penetration is defined as the presence of an electron inside the shells of other electrons. It's important to know that s orbitals are more penetrating than p, and p are more penetrating than d, etc., etc. And so this is actually why our electron configurations that we learn in general chemistry are the way they are. It comes from penetration. So as a result of shielding, the order of the energy levels in many electron atoms are usually like this. You know that the s orbital is lower than the p orbital, is lower in energy than the d orbital, etc. So let me ask you, if you look at your periodic table, when you put the second electron in helium, okay, you know that it should go into the s orbital, right? When you have an atom like lithium, you know that you put the first electron in the second shell into the s orbital. But why not the p? we've learned that the s orbitals are lower in energy than p orbitals. But we never really were explained why. Okay? The reason is penetration. So we just talked about the fact that the closer an electron is to the nucleus, the lower in energy it was. I don't think I said it specifically that way, but the more positive charge it feels from the nucleus, the lower in energy that electron is. So if we look at the radial distribution functions, here we go, of a 2s and 2p. And I don't like this particular chart because it doesn't show the 1s. But I'll draw in the 1s. The 1s looks like this, something like that, okay? So if you look at the total function of the 2p orbital, it looks like it's closer. So if the nucleus is over here at 0 distance, right, the 2p radial distribution function looks closer to the nucleus than the 2s. But the 2s has a special ability to penetrate, and that's shown right here. So the 2s orbital actually is closer. It has some of the function that's closer to the nucleus than the 2p orbital. So the 2s orbital penetrates more than the 2p orbital into the 1s. Following? Okay? So that's what makes the 2s orbital lower in energy than the 2p orbital, because it can approach the nucleus approach the nucleus much better than the 2p orbital, and so it is a lower in energy orbital. This is why we have this trend. Now, this is true, I want you to write in your notes that this is especially true when Z is greater than or equal to 21. What element is that? Where is that on your periodic table? Yeah. So when you are at 21 or greater, this is the trend that you see. But it's not always the trend. So we learn that our electrons feel like this. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, right? The 4s orbital fills before the 3d. And that's because the 4s orbital can penetrate better than the 3d orbital can. So this is true in the hydrogen atom. And this is true when we're dealing with our smaller atoms. So let me show you now another figure from your textbook. So this figure can be a little confusing at first, but what you're seeing here is the s orbitals, p, d, f, and their relative energy levels. So if you look at so we're going to focus on the 4s here and the 3d. So the 4s here and the 3d. So for Z less than 21, notice that the 4s orbital is in fact lower in energy than the 3d orbital. But the higher we get in number, Z after 21, so scandium and greater, your 3d orbitals are actually lower in energy than your 4s orbitals. And so the trends that we've learned are actually still true, but it's not because the 4s orbital is lower in energy than the 3d orbital. So in hydrogen atom, 4s is in fact lower in energy than the 3d. But in elements where you have a Z greater than or equal to 21, the 3d is actually lower in energy than the 4s. They are close in energy, but they're lower. The bigger atoms have even bigger differences in the 3d and the 4s. So the bigger you get, the farther you go along the periodic table, the lower and lower the 3d orbital gets in energy. Okay, so why do we care about this? I'm going to assume that you understand ground state electron configurations as you've been taught them before. So hydrogen is 1s1, helium is 1s2, etc., etc. I can draw carbon as helium 2s2, 2p2. And I'm going to assume that you know the Aufbau principle, which is the building up principle. You always put electrons in lower energy orbitals first. Hund's rule, when more than one, you can basically put parallel spinning electrons in orbitals of equal energy, and you put them in individual electrons before you pair them up. And the Pauli exclusion principle that you can only have 2 electrons in. So these are our electron configurations, and for the most part, you can follow the trends, except in a couple cases. So all of your exceptions will happen with the transition metals. And I'm talking about transition metal atoms, okay? Not the ions, but the atoms when I'm talking about these trends. So the first exception is when you have atoms with partially filled d shells. So I'm talking about scandium, titanium, vanadium, or anything underneath. And anything in this transition block except for zinc, cadmium, and mercury, which have full d shells. When you have partially filled d shells, in those elements, is the d orbital higher in energy or lower in energy than the 4s? Based on what we just talked about. The d orbital should be lower in energy than 4s. But the 4s orbital actually does fill first. Isn't that weird? For the atoms with partially filled d shells, we explain this by reasoning that there must be an energy benefit to putting electrons in the 4s orbital, right? And the energy benefit comes from the fact that the 4s orbital is larger and there are less electron-electron repulsions in that particular orbital than if you would put the electrons in the 3D together. So the justification for our trend is that for atoms with partially filled d shells, because of the fact that we have observed spectroscopically that the 4s orbitals are occupied, we think it's advantageous to occupy orbitals of higher energy, like the 4s, because it reduces repulsions between electrons in the 3D. Now, you will notice in your textbook that the electron configurations are often written with the 3d orbital first. So they will be written 3dn 4s2. The reason for that is because the 3d orbital is actually lower in energy level, and they're trying to show that by writing 3d first. The way that I learned it when I was in Gen Chem is that I would always put 4s2 first. I would fill them, or I would write them in order of filling, but you'll notice that in this textbook, they do the lower energy level ones first. I don't care how you do it. I think it's useful to write 3D first to remind myself that it's a lower in energy level, but it's okay if you want to write it the other way. But our trend holds, and this is the same way that you learned it in general chemistry. The 4s2 orbital does in fact fill first, but it's not because it's lower in energy level. The second exception is for half-filled or fully filled d shells. So for half-filled or fully filled d subshells, there's a special energy benefit for half-filling or fully filling that shell. And it's due to something called spin correlation. So I'm going to write down half-filled or fully filled d subshells have special energy benefit due to spin correlation. So I'd like you to tell me, without looking too closely at your periodic table, what would you expect the electron configuration of chromium to be, based on what you have learned before? Would you have expected it to be 3d4, 4s2? Mm-hmm. Okay. So there are 5 orbitals in the d shell, and when you have 1 electron in each of those orbitals, so I'm going to write them over here. So I'm going to write my 5 d orbitals. When you have that shell half full, so that all the spins are pointing in the same direction, there's an energy benefit to that. And so you will take one of the electrons out of the s orbital in order to fill that d shell, or half fill that d shell. Another example is copper. So the electron configuration of copper is this, rather than what you might expect, which is 3d9 4s2. And again, that's because there's an energy benefit for completely filling this D shell. Okay, so let me really point out that these, again, we are talking about the atoms, not the ions. So anytime that you're dealing with a transition metal element in a complex, so something other than just the atom, in a complex or an ion, you always put the electrons in the D shell because they come out of the 4s shell first. So if I were talking about an iron 2+, the 2 electrons that leave the iron come out of the 4s shell. If you were talking about an iron 1+, you would still take 1 electron out of the 4s, and the other electron would go to the D shell, usually. So it's kind of it's different rules for ions and for atoms. For atoms, it's a little harder and trickier, but for ions, it's pretty easy. So other notable exceptions that I want to mention are the fact that the second and third row transition metals don't follow the same rules. So they both have trends, so they both follow trends, but not the exact same rules. So for example, if you take that periodic table that I gave to you and check out the transition between iron and zinc versus ruthenium to cadmium. Put the electron configurations, compare the electron configurations in the same families between those 2 rows. Do you notice anything? Are they the same? Electron configurations, like between iron and ruthenium, for example. Yeah, so with ruthenium, you have 4d7, 5s1. So iron makes sense to me based on those rules, but then why 4d7, 5s1? How can you rationalize that? And if you look at rhodium, you have 4d8, 5s1. And then for palladium, you have 4d10 instead of, for nickel, you have d8s2. So is there anything that you can use that we just talked about to rationalize why that would be?
5s are much higher.
Yeah. Okay, so the bigger the atoms get, the lower the d orbitals actually get compared to the larger shelled s orbital. So the 4d orbital, so if you compare the 4d to the 5s orbital energy levels, that's going to be a bigger difference than the 3d to 4s. So the changes in these trends are due to the difference in energy levels between s versus d orbitals. Let me just ask you one more question. So if the d orbital, the 4d orbitals are so much lower than the 5s, why would you put any electrons in the 5s for ruthenium and rhodium? How can you justify that? Any ideas? So how did we justify that the 4s orbital got filled first in the first place, before the 3d? Even though the 4s orbital is higher in energy than the 3d orbital, why does the 4s orbital get filled first? Yeah. Repulsion. Yeah, in order to reduce electron-electron repulsion. So that might be a good reason why there's any electrons in the 5s orbital in ruthenium and rhodium, even when the 4d orbital is much lower in energy. Because there is always an energy associated with putting orbitals in the same, or electrons in the same orbitals, or in the same shells, and with pairing them as well. Okay, so one more notable exception is the fact that the lanthanides, there are exceptions to the trends that we've learned. So for lanthanides and actinides, actually. So not only with electron configuration, but also with the size of the atoms. But first, let's look at the electron configurations, and just let's use La and cesium. So I've written the electron configurations that they actually have up here, the expected one based on our trends. So just like the relative changes in the d and s orbitals give weird things with transition metals, the f orbitals also have some funky things about them that changes the trends. And let's look at the atomic sizes of these guys real quick and compare them to what we would expect. Let's actually just start by talking about the d orbitals. If you look at the difference in size between carbon and silicon, notice there's a huge, it's a pretty big difference between the size of those two atoms. And you'd expect, as you go up in shell number, you always get bigger. But when we get up in shell number here, it didn't get very much bigger. It's actually almost the same size. And the reason for that is because even though there's many more electrons in this element, most of those electrons are in the d shell. Because the d shell doesn't penetrate very well into the s orbitals, it doesn't actually reduce the effective nuclear charge very much. And so the s orbitals in the very center of the atom are still contracted a lot. And also the outermost electrons are not shielding each other as much. And so you have an overall contraction of this atom compared to that guy. Okay? So this guy, all of the electrons are really shielding each other here, but not quite as much here. So a much more of the full nuclear charge is felt on the outermost electrons. And the same argument can be said for the f orbitals, and that's why we have something called the lanthanide contraction. So if you notice, so here you've got a pretty big atom, and there just isn't very big difference. Even though these atoms here have many, many, many more electrons, you just don't have the huge jump that you might expect based on how many extra electrons they have. And it's because those f orbitals are not very penetrating, and so they don't have a very big effect on the effective nuclear charge. Okay. So let's just review quickly our periodic trends. As far as atomic radius goes, we just talked about the fact that the atomic radius decreases when you go from left to right. So I'm going to draw my cartoon of a periodic table here. Over here on the very top right-hand corner, we're going to have the smallest atoms. And down here, we're going to have the biggest atoms. Across, we decrease in size. And going down, what happens? We get bigger. Now, the exceptions to this trend, I'm going to pull up my periodic table again. Exceptions here aren't very obvious on this table, so I'll just write them. At D5 and at D10 in the first 3D shell, the trend is not followed, and in the lanthanides. Now, we've been talking about atoms. What about positively charged ions? If you take an electron out of an element, what do you think is going to happen to the size? What? What? Exactly. Yeah. So all positively charged ions are going to be smaller than their respective atoms. And the negatively charged ions are going to be larger. So the ionization energy. Now, consider shielding and the size of the atom. Ionization energy is the energy that it takes to remove an electron from an atom. And the closer the electrons are to the nucleus, the more of that nuclear charge they feel. So it might make sense, I hope, to you that the ionization energy trends are actually opposite to radius. So the smaller the atom, the harder it is to remove that electron. Whereas the bigger the atom, the easier it is to remove the electron. So some things to note. The ionization energy is proportional to the square of the effective nuclear charge. And as the Z effective increases, the ionization energy will increase across a row. This ionization energy is also proportional to 1 over the square of the shell. So as the shell number increases, ionization energy decreases down a column. And ionization energy is also proportional to 1 over the atomic radius. So as the radius increases, ionization energy decreases. Electron affinity. This is defined as the enthalpy of gaining an electron. technically the electron affinity is the enthalpy of gaining an electron. And so a large negative enthalpy of gaining an electron is where the negative ion is more stable than the atom. So the trends in electron affinity should probably be familiar to you. They increase going up and across the periodic table. So fluorine has the highest electron affinity. And this is very closely related to the electronegativity. The electronegativity is technically the power to attract electrons to itself when it's part of a compound or when it's part of a bonded molecule. So it's the power to attract electrons when the atom is part of a compound. There are 3 different definitions for electronegativity. All of them are different in only slight ways. You can read about it in your textbook. I don't need you to memorize it as long as you understand what electronegativity is and its trends. And then the last thing I want to talk about is polarizability. And this is a really important one to understand, especially later when we start talking about hard, soft, acid, base theory. Polarizability is basically the ability of the atom to change the direction of its dipole moment. That's the technical definition. But its ability to polarize its electron cloud or respond to a polarizing agent. This happens when there are a lot of empty orbitals that are close in energy, where electrons can move around to different spots. So it tends to be large atoms are very polarizable. So as you go down in the periodic table and you increase in size, you increase your polarizability. However, when you go across the periodic table and you're decreasing in size, you're also decreasing your polarizability. So it really does correlate to the size, and it's important that there's a small gap between the HOMO and the LUMO. So large atoms and ions are easily polarized. Small atoms and small ions are not very polarizable, but they can cause polarization. So they're said to be polarizing because they are very small, concentrated centers of charge, and so they will cause polarizable atoms to be polarized. And atoms without a noble... So when you were talking about positive ions that have a noble gas configuration, so we're talking about things in... this isn't very pretty, but the things in the first 2 families of the periodic table, so your alkali earth metals and your earth metals, those positively charged ions have a noble gas configuration. They're not very polarizable. Other positively charged ions without noble gas configuration are easily polarizable. So that's where we're talking about transition metals. So I think of the atoms or the ions that are easily polarizable, I think of them kind of as a squishy kickball, where you can squish one side of them and move electron density to the other side, or air. Whereas like things that aren't polarizable would be like a baseball. They're really hard, they're compact, all of their electrons are very compact into a small center. Okay. So that's all I had to talk about periodic trends. The assigned reading is for Chapter 1 and for Chapter 9. It's only about the first half of Chapter 9 that has anything to do with periodic trends. It's pretty closely related to what I said, but there's a little bit more detail. So if you have the desire, please read those chapters. It's most important to try to do those problems in the chapter just to get practice. And then book me if you want my help. And if you go in there and someone's already booked me, that means I'll be here.